Hello, everyone. Today, we are diving into one of the core principles of classical mechanics, that is D'Alembert's principle, and we'll learn about its application in plane motion and connected bodies. This principle plays a very crucial role in understanding how forces work in systems, particularly in case involving dynamics. Now, Jean Leron d'Alembert was a French scientist, philosopher, and writer who discovered the principle. This is now known as d'Alembert's principle. D'Alembert's principle is a fundamental statement of classical laws of motion that relates to Isaac Newton's laws of motion. It was published in 1743 in D'Alembert Treatise on Dynamics. So, Jean Leron, who was a French mathematician and scientist, philosopher, and writer, discovered this D'Alembert's principle. And in the coming slide, we'll also see that how the principle is related to Newton's law of motion. Now, inertial force. Inertial force is defined as the force which is in the opposite direction of the accelerating force and is equal to the product of the accelerating force and mass of the body. So, inertial force is when an unbalanced force is applied to an opposite direction of accelerating force, and inertial force is equal to the product of the accelerating force and mass of the body. Now we'll see why D'Alembert's principle is used to study the plane motion. Let's see. For the system, especially moving in plane, especially those with rotation and translational, D'Alembert's principle simplifies the analysis by introducing inertial forces that accounts for both translational and rotational motion in an equivalent static framework. By considering inertial forces, we can separate rotational effects from translational ones, making it easier to analyze how forces and torque interact. So, D'Alembert principle it simplifies the both the transitional and rotational by introducing an inertial forces. Okay, so by considering that inertial forces, we can separate the and rotational effect from the transitional one. So now we'll study what the D'Alembert principle states. So the principle basically states that the sum of the difference between the applied force and the inertial force, which is also called as fictitious force on a system of a particle, is zero when the system is in dynamic. So basically, when a body is kept at a state, the applied force, for example, we can say as F, and the inertial force as ma, that is minus ma, on a system of particle is actually zero when the system isn't dynamic. Now, this principle also allows us to analyze the dynamic problem using methods similar to those in static analysis by introducing that inertial forces. So actually, D'Alembert's principle is very helpful by introducing that inertial forces as it analyzes the dynamic problem into a static one. So now here are the two examples which I'll explain. To give an example of dynamic and static, for example, the mobile we're holding to watch this video or a laptop kept on the table is in a static equilibrium, which means it is a static. There are a lot of forces acting on a mobile, but it is in a same position without any movement. Whereas on the other hand, dynamics are all sort of movement you see. For example, here the cars are moving. Okay, so this is the difference between static and dynamic. Now, what is use of D'Alembert's principle? So this is a stationary body which is in rest, and this is the body which is in motion. Here you can see force is applied and with mass into acceleration. So basically what has happens is that this D'Alembert's principle is always easy, and it helps to solve the problem of statics than dynamics. As you can see that because of dynamics involves a lot of parameter which complicates the solution, so it is very easy to solve a static one. So D'Alemberts help us reducing a problem in dynamic to a problem in static. So also we can convert a dynamic problem to a static one. And also D'Alembert's principle is the alternative form of Newton's second law. Now to understand the D'Alembert's principle, let's start with Newton's second law of motion. So, we already know this. The force F acting on a body is equal to the product of the mass, that is m, and acceleration of the body, that is a. Or we can say F equal to ma, which is the equation of the Newton's second law of motion. Now we'll watch a video and I'll explain you with the video as the video is starting. So MA is the force behind the motion of the box. Here now, according to D'Alembert's principle, we need to consider the whole system and apply another force minus MA in the opposite direction of the original force MA. This will bring the system into static equilibrium. The force minus ma is called as inertial force. In D'Alembert's form, the force m plus the negatives of the mass m times acceleration a of the body is equal to 0. In other words, the body is in equilibrium under the action of the real force, that is F, and the fictitious force is also, and minus a is also called the fictitious force. The fictitious force is also called as inertial force and reverse effective force. Now, D'Alembert's principle applicable to plane motion. So, we know that D'Alembert's principle is also applicable to plane motion, as obviously it's like, so let's just consider that a body of mass m with moving with uniform acceleration under the action of external force, that is F, which is also known as effective force, then according to Newton's second law of motion, we have, that is F equal to ma. The equation 1 can also be written as, taking that ma at the left hand side, we can write as F minus ma equal to 0. Now, considering equation 2, it is very clear that by applying a force minus ma on the body will be in equilibrium, as the sum of all forces acting on a body is 0. Such equilibrium is called dynamic equilibrium, and the force minus ma is called as D'Alembert force or inertial force. We have already seen this. So therefore, it states that the resultant force acting on a body together with the reverse effective force or inertial force are in equilibrium. The body will be in dynamic equilibrium under the action of external force F and the inertial force. Hence, D'Alembert principle states that the net external force acting on the system and the resultant inertial force are in equilibrium. This is D'Alembert's principle applicable to plane motion. So basically here says that When let's take a body of mass m moving moving with uniform acceleration, okay, acceleration under the action of the external force F. Then according to Newton's second law, we can write this that is F equal to ma. Then equation 1 we can also written as F equal to minus ma, which gives a very clear equation, that is this that is the body will be in equilibrium as the sum of all the forces acting on a body is zero. We can see that. So such equilibrium is called as dynamic, and this force as minus ma is called as D'Alembert force or inertial force. So the body will be in dynamic equilibrium. It also states that the resultant force, that is F equal to minus a with that is with the reverse effective force, that is minus ma or inertial force, are in equilibrium. So now here it's D'Alembert's principal mathematical representation. You can see here. So the principle can be explained mathematically in the following way. That is sub summation I f bracket fi minus mass into acceleration del ri equal to 0, where I is basically the integral used of the identification of variable corresponding to particular particle in the system, and fi is the total applied force in the ith place, and mi is the mass of the ith particle, and ai, which is the acceleration of the ith particle, and mi into ai is the time derivative representation. Del ri is the virtual displacement of ith particle. So basically, virtual displacement is refers of a system refers to a change in the configuration of the system as a result of arbitrary infinitely change of the coordinates. So now we'll study about what principle of virtual work is. So the principle of virtual work basically states that when an object is in equilibrium, the virtual work done by the force on the object will be equal to zero. The same is stated in Newton's laws, which state that the applied forces are equal and opposite when at equilibrium. So the virtual work is when an object is in equilibrium. The virtual work done by the forces on that object will be zero. Okay. The same is stated for Newton's law when an applied forces are equal and opposite when at equilibrium. Okay. So here I have done some derivation on D'Alembert's principle. As you can see here, this is a body type and Ri is the vector. So it's basically the definition of the virtual displacement. That is, virtual displacement of a system refers to a change in the configuration of the system as a result of the arbitrary infinitely change of the coordinates, and del r is the consistent with the forces and constant imposed on the system at any given instant of time. So here time is basically constant, and we know that work equal to force into displacement. So here I just wrote it is work done equal to fi into d, and work equal to summation of fi into, we know that del r is consistent, so like just write in here del ri. So this is the equation 1, and if the system is in static equilibrium, that is, we can say like it's like static means like no work done actually, so like del fi equal to 0, and we can also write this as a del r dot I. Now by the principle of virtual work, as we have already seen in previous, so work throwing, So F summation of Fi equal to del F Q and plus F. Then we can see how it is solved here. It's the mainly the equation part. Now by having that using equation of motion where we can say is F equal to dp by dt, where we can consider p as mass in as momentum. Okay, this mass into, we can say, as velocity also, or acceleration. So Fi equal to, by differentiation we can say Fi equal to pi. Now taking pi this side, we can say Fi minus pi equal to 0. Now from the earlier equation 3, when consider summation Fi minus Pi del Ri equal to 0, which is the D'Alembert's principle. Now here we can see like 1D motion of rigid body, that is T minus W equal to ma, as you know, like, or we can say like T equal to W plus ma, where we can say like T is a tension force, which is we already have discussed before also. So like T is and W is basically the weight of the sample model, and ma is the acceleration force. It is usually helpful in 1D motion of a rigid body, for example when it is in plane motion. And if it is a 2D motion, like many solid like cubes and all, so we can say for an object moving in xy plane, like considering the xy plane, the following of the mathematical representation is Fi equal to m minus mrc, where Fi is the total force applied on the ith place, and m is the mass of the body, and rc is the position vector basically of the center of mass of the body. So this is basically an example on dynamics. So here this man is pushing a body, which is basically a example of dynamics. So now we'll discuss about the importance of D'Alembert's principle in mechanics. Why is it important? So I guess the first point is very clear, because we have discussed this multiple times. Like basically, D'Alembert's principle transfer a dynamic problem into a static equilibrium. So D'Alembert principle rephrases dynamic equation by introducing that inertial forces, which is that minus ma. This turn a problem involving motion or acceleration into one as resembling static equilibrium. As a result, we can use static equilibrium method, make it easier to analyze systems that would otherwise be complex to solve. So as a result, we use the static equilibrium. So thus, it helps us to solve from the complex one to simple. So now we can say like D'Alembert's principle applies to both particles and rigid bodies, as making it versatile for use in engineering and physics. It's like too common because like D'Alembert's principle is where multiple bodies interact, like linkage, machineries, etc. Now, why D'Alembert's principle is used for system with connected body? So first point is like work well with constraint. Many connected systems such as linkage and mechanism such have constraints that restrict the movement of component relatives to each other. Now D'Alembert's principle incorporate this constraint naturally, allowing each body forces and the motion to be analyzed in a unified ways. So there are many linkage and mechanism, but D'Alembert's principle just restrict the movement of the component relative to each other. Okay, and basically D'Alembert's principle simplifies, analyzes the interconnected forces. Therefore, the connected bodies, you can say many are connected bodies. For example, you can say exert forces on each other that are often difficult to calculate. Now, by introducing that inertial forces, D'Alembert's principle treats us as a system in equilibrium, making it easier to find these forces with solving complex dynamic equation. Now here you will see for like this principle is basically applicable for the plane motion also. So we have this one which is the analysis of the motion of two bodies connected by string. You can see here string are connected and two bodies. So let me explain. So two bodies of weight W1, which is here W1 and W2 are connected to the ends of a light inextensible string passing over a smooth pulley. So there's a smooth pulley and these are the strings. So the weight W, as you can see, W1 is more, the string is more here. So it's like basically visible. So the weight W1 is more than W2. And now, as we know, let A be the acceleration of the system, as we know. Okay? Now, the external force acting on a system in the direction of motion is basically, this one is bigger, right? So W1 minus W2. And we know that the inertial force is mass into acceleration. So we can also write as mass of W1 as like mass is basically weight by gravitation, acceleration, gravity. So it's like it minus W1 by G into A. Now, the same for the inertial force on weight W2, that is minus W2 by G into A. Now, by like adding this equation, okay, so we get that is minus A by G bracket W1 plus W2. In here, we take like, we just into it and we just crisscross it and it's just come, the equation will come out. So, but according to D'Alembert's principle, the net external force acting on the system and the resultant inertia should be in equilibrium. So the net external force, we know like it is obviously it is W1 minus W2, as we have already here done it, and plus the resultant inertial force, that is this. So by taking this two, we find the acceleration as G bracket W1 minus W2 bracket divided by W1 plus W2. Same here, but here the bodies are connected by a string when one body is lying on a smooth horizontal surface and the other is basically hanging. So this is a smooth one and the other is basically hanging. So here also let A be the acceleration of the system. So the net external force acting on this shown as W in the direction of W1. So here W2 is not acting as the weight of the W2 is not acting as the direction of motion. Okay, W2 will not act as the direction of motion. So similarly here also inertial force on weight W1, that is mass into acceleration. Mass we know that is W1 by G into acceleration, and inertial force on weight 2 is similarly minus W2 by G into acceleration. Now here you will see like this force will be acting on W2 in the opposite direction of W2. That is, this force acts in horizontal direction towards left of W2 and will pass through the center of gravity of the body of weight W2. So minus W1 by G into A plus minus W2 by G into A, by adding this, we get minus A by G bracket W1 plus W2. But according to that D'Alembert's principle, the net external force plus the resultant inertial force should be 0. So now as we know, like net external force is only W1, so we take only W1 and the total equal to 0. So from here we get A equal to GW1 divided by bracket W1 plus W2. I guess it's clear because there are two types of analysis. For the first one, it was when two bodies is connected through a string. But for here, it is when one body is lying on a smooth horizontal surface and the other one is hanging. So therefore, only one weight is taken and the other weight is not taken, as it is only lying. Now here we'll see like how the motion on an inclined smooth surface. It is also same, but yeah, like it basically shows a body of weight, okay, W, sliding down on a smooth inclined surface. So this is a smooth inclined surface basically. So this is a smooth inclined surface, okay. So let's say like theta, that is this theta is equal to the angle made by the inclined plane with horizontal, okay. This is the angle made by the inclined plane with the horizontal, and W is basically the weight of the body, and we can A is the acceleration of the body, and from here we can like say like mass of the body is equal to weight by G, okay. Now, as the surface is basically smooth, therefore the frictional force is actually to, sorry, my handwriting is very bad. I don't know why. Hence, the forces acting on a body are its own weight, that is W, and the reaction which is acting on the of the plane, okay. So by getting the resolved part, by taking W as a perpendicular to the plane, we can say like W cos theta, which is like, theta. So that's why. And W sin theta to the x-axis, okay. And with W cos theta, which is balanced by R, while the other, which is parallel to the plane, which is W sin theta, which produces acceleration down the plane. Therefore, the forces we can say that is F equal to W sin theta, that is down the plane. Now, using the equation, we have F equal to ma. Now, substituting the value, that is F and m, we get, that is, we have now F equal to ma. So F we know like W sin theta, and plus m we know like W by G, means like weight by gravity of acceleration into acceleration. So we get that is A equal to G sin theta. Now, if the body is moving up the plane, corresponding the acceleration will be minus G sin theta. Because when the body moves down, the acceleration basically becomes G sin theta. But when it is up the plane, the acceleration becomes minus G sin theta. Okay. Now, similarly, for an inclined rough surface, the shows a body of weight W sliding down the rough inclined surface. For example, we can say like let A equal to acceleration of a body, okay, and m equal to mass of the body, that is W by G. Inclination of the plane with horizontal, and theta is the inclination of the plane with the horizontal, and mu is the coefficient of friction, and F1 is the force of friction. As the body is moving down the plane, there's a force of friction will be acting up the plane, okay. So F1 equal to nu R. Nu R means the reaction, and nu plus R, we know this equation as R equal to W cos theta. So we can write as nu w cos theta. Now force acting down the plane, which is F2, and it's F2 equal to W sine theta. Now the total forces, which is F2 minus F1, that is W sine theta minus nu W cos theta. Okay. Now using this equation, F equal to ma, we get, like, we can take this F from here. Okay. So this W sine theta minus nu W cos theta equal to W by G into A. Okay, as we already know, this mass is like W by G. So taking W common, sine theta minus nu cos theta and W by G into A. Okay, so we have by like cancelling this W, we have by taking this G this side, we have G by G bracket sine theta minus nu cos theta equal to acceleration. So now let's do some numericals. So this is basically a question which I'll just read it here. Let a body of mass m1 resting on an inclined plate is connected by a string of pulley to another block of mass m2 as shown in the figure. Find the tension in the string during the motion of the system. Assume the coefficient of the friction between the block M1 and the inclined plane to be 0.2. Assume M1 and M2 as 150 kg and 100 kg respectively. So here it's basically given that M1 equal to 150 kg and M2 equal to 100 kg, and coefficient of friction is nu equal to 0.2. So as we know, like, it is connected by a string, so this box we can say, like, as it is like mass is 100, M2's mass is 100, so we can take the like weight as is like m into g, right? So we can take is like 100 into 9.81, that is gravitational force, so like 98.1 Newton, which is the weight. Similarly, if this one is 98.1 total, so here it's like a tension, and from here the weight will be like divided, so this both it's spatially equal one, so 490.5 Newton here and 490.5 Newton here. So and here also a tension is creating, right? They're both, a tension is creating. So now as we know, like, frictional force equal to nu into normal reaction, so like nu is nu 0.2 and normal reaction, I guess we get, cause like C, okay, so this one will be 490.5.5, and the so this box is mainly 150 into G, right? So 150 into G basically is 9.81, that is the gravitational force, and it becomes 1471.5 Newton, which is the weight of M1. So taking both the side components, that is 1471.5 sine 45, and taking here components, that is the y side components, that is 1471.5, that is cos 45, as we have this also as 45 degree. Okay, this one is 45 degree cause this one is inclined, so we know by alternative angles, so this one is 45 degree. So that is 150 into 9, that is so where I was, yeah, So this 1471.5 sine 45 is basically 104.5 newtons, and similarly here also 1040.5 newtons. So we actually need to find both the acceleration and the tension. So we know the direction of motion. So this one is already we calculated. So for the case one, which is in the forward direction, we can say like left hand side, we take it as like 1040.5 plus 208.1, that is the frictional force, and now LH is equal to 1248.6 Newton and RH is equal to 490.5. So here it says like LHS is greater than 495, which is it will move downwards. And similarly here also we can say like LHS is 1040.5 and RHS is 490.5 plus 208.5. Okay, so it's like 698.6, and where LHS is greater than RHS. So acceleration relation between block 1, so it will also move downwards. So like LHS is greater for both the cases. Okay, an acceleration relation between block 1 and block 2 is like the total length of the string, that is L equal to x plus 2y. It comes like, see, this is the total length of the string. Okay, and from here to here we can say it's y, we can say it's y, and this one is x. So it's not only this y, but we have to say this y also. So there's 2y plus x. So now differentiating this equation with respect to t, we get dl by dt equal to dx by dt plus 2 dy by dt. So we can keep this dl by dt equal to 0, and dx by dt we can write as v1 minus 2v2. So v1, taking 2v2 that side. Okay, so we have v1 equal to 2v2, and we know like acceleration is equal to actually velocity. So like a from the equation, like a1 equal to 2v2. Now motion analysis. Now like taking like each one. So we have here x component, which is mass into acceleration, and we get this like, it will obviously like take in the, it is a tension frictional force having x and y components here too. So basically what I take is like for this one, so 1040.5, okay, minus t, that means this side, and minus 208.1. So, and by taking 150, that is mass, and a1 we don't know. So, and 104 is this side. It is positive. Okay, it will be positive. So now adding this, we get this as 832.4 minus t equal to 150 a1. So basically tension is 832.4 minus 150 a1. And for similarly for this also, like for the y components, we get that is fy equal to m2 a2. So 2t minus 981, as we know this is the weight. Okay, so this is the weight, and mass is basically 100 into a2. So 2t minus 981, again by taking that equation we know that like a1 equal to 2a2. So keeping this in mind, we write here and we get this equation. Now put in this one equation in equation 2, like putting this t in equation 2, basically get the a1 value as 1.953 meter per second square, and acceleration for 2 as 0.9765 meter per second square. And also by equationing we get this tension equal to 539.3 Newton. Now, now we also have a second problem we'll discuss, which is two blocks of masses m1 and m2 are placed on two inclined planes of elevation, that is theta 1 and theta 2, and are connected by a string as shown in figure. Find the acceleration as the masses. The coefficient of friction between the blocks and the plane is nu. Assume m1 equal to 5 kg and m2 equal to 10 kg. Theta 1 is 30 and theta 2 is 60 and nu is 0.33. So for this diagram, first we need to make an FBD for different blocks. So we just made FBD of block M1. So this one is block M1. We can see acceleration is in upward direction. Tension, obviously there is a tension in this string, and we know that this is theta 1. So taking this here, theta 1 is 30. So taking this angle 30, and there is a normal reaction there. Then we have this mass m1 into g, which is mass into gravity. And now here we have m1 g sine theta, which is the components. Okay, so nu n1 minus t, that is nu n1, as we have this frictional force, so nu n1, and here is like minus t plus m1g sine theta, as this one is this side, so it's like positive and this one is like negative part. Okay, and equal to m1 minus c, as acceleration is in this direction. Okay, so that's why acceleration in this direction. So now by taking the y components, we have n1, okay, and minus m1g cos theta, as we know, like this one is obviously m1g, so like just making the direction, so minus m1g cos theta, so n1 equal to m1g cos 30, sorry, cos 30. So now by taking this two equation together, by taking the n1 here, so we get that is t minus m1a equal to nu m1 g cos 30 again plus m1 g sin 30. Okay, now for the second one, that is for the block m2, we did the same. Okay, here again normal reaction for the block m2, then the weight, that is m2 into g, and divided the components, we get that is m2 g sine theta. Here also we'll get as cos theta, and acceleration is this side, and then we get also tension. So taking this like as x component first, so summation of x fx equal to ma x side, so we get that is t this side, t will be positive, plus nu n2, that is frictional force here, and minus m2g sine 60 is this side, this is minus m2g, and equal to m2 minus a is obviously like acceleration will always be like for this question will be minus. So again for that y components, we have this may, that is n2 minus m2g cos 30. Now put in that n2 here, we get this, that is t plus m2a equal to m2g sine 60, again minus this equation. Now on solving this equation and the earlier equation, we get that is acceleration equal to 2.014, and they ask us to find the acceleration only, so that's right. Now the application of D'Alembert's principle. D'Alembert's principle is basically based on the principle of virtual world along with the inertial forces which already we learned. So the following are the application of D'Alembert's principle: mass falling under the gravity. Okay. Then we also learned parallel axis theorem in center of, I mean in moment of inertia, I guess. Huh. That's one. And frictional vertical hoop with the beads. So thank you.